All right, and we continue. We're almost halfway through. All right, so I'm going to skip some of these. 42 is just a direct kind of looking at the z-score table. So that one's 98.93 because the z-score is 2.3. It's pretty direct. This one is a good little definition question. Basically, this rule 68, 95, 99.7 works if you have integers 1, 2, 3, 4, etc. All right, so we will get number 44. Number 44, it says use the table below to answer the question. So I am glad for this class that they kind of give you a piece of the z-score table. It makes it a lot easier than having to carry around a sheet of paper about the size of a full sheet with all these numbers and having to figure it out from there. So this is really nice. So the number is 2.3. I'm looking for 2.3. 2.3 is right here. The number up top, they say z-score, that's the number 2.3. And then in this question, they want both the data that lies below and above. So the number given is what lies below. That's 98.93. To get the amount above, I would do 100 minus 98.93. Okay, so let's see, 100 minus 98.93 is 1.07. So it's not much. That is the answer. Okay. Similar question. The percentage of data items in a normal distribution that's between 1.2 and 2.4. So I am going to highlight both of those. 2.4 is right here. And then 1.2 is right here. To get the data between, you simply subtract the bigger number, the smaller number from the bigger number. So 99.18 minus 88.49. Now, if you had messed up and you had done 88.49 minus 99.18, just take the absolute value. All right, that's 10.69. $46. So again, we have a z-score table, but the difference here is we have to find the z-scores. That's okay, fine. So this is 46. First thing we got to do is find the z-scores. Okay, so we got to find both of them because they want to know between 158 and 176. So for x equals, which one is bigger, 176, and x equals 158. I'm going to use my formula. My formula, remember, is x minus x bar over s. And so I plug both of those in. For this problem, they tell me my mean is 130. My standard deviation is 20. Okay, so I'm using those values for both of these. Okay, for both this and this. So the z for the 176, that's kind of how they label it, is x, which is the 176, minus x bar, which is 130 over 20. Okay. So we got to find the z-score. 176 minus 130 divided by 20. I get 2.3. Okay. The z-score of 2.3 is right here. I'm going to highlight that. Okay. And now I have to find the z-score for the other guy, which is 158. Okay. So 158 minus 130 is 28. Divided by 20 is 1.4. So now I need to find the z-score of 1.4, which is here. We want to find what's between, so we have to subtract. Okay, the z-score of 1.4 was 91.92. The z-score of 2.3 was 98.93. Okay, I could say z sub 158 and z sub 176. And these are the numbers we need to subtract. Okay, so 98.93 minus 91.92. 98.93 minus 91.92 is 7.01. So 7.01%. Number 47. Same kind of question, similar question. Not the same. This one says we have to, first of all, we have to find the z-score again, but we're looking for a percentage that weighs more than something. Okay, so we got to first find the z-score. So this is 47. We got to find the z-score and then find the percentage below, and then find the percentage above. Okay, so here we go. We got to do the z-score game again. Z is x minus x bar over s. In this problem, let's write down what they give us. Doesn't matter for the problem how we work it, that it's 18-month-old. All right, we care about the mean, x bar, 24.7, and the standard deviation of 2.2. Now, this 26.8, that's our x. So x is 26. Just plug it in. Z is 26.8 minus 24.7 over 2.2. 26.8 minus 24.7 is 2.1 over 2.2 is a number that goes on forever. 95455 forever. All right, well, when I look for z-scores, that's not on there. So this is a z-score. This is, I need to round a z-score to, it looks like 1 decimal place. Okay, I'm gonna round it. So round to 1 decimal place. All right. Well, what happens if I have this number and I round that to 1 decimal place? Well, it gets rounded up to 1. That's kind of weird. All right, so my z-score is 1. I look for 1, and here it is. But the question says we're looking for weighing more. So the percent that weighs less is 84.13. But the question wants which weighs more. So the percent that weighs more is 100% minus 84.13%, which is not much. 15.87. Okay. That's it. It's a tricky one. Okay. 15.87. All right. Number 48 says the table to the right shows the selected ages of licensed drivers in one country and corresponding percentiles. All right. Find the percentage of drivers who are at least 45 but less than 75. So find 45 and I need to find 75. Okay. They want us to find the difference. So 98% minus 63% is 35%. Yeah, that one's, compared to the other two we just did, that one's relatively easy. 48. 49. So we now are officially into chapter 14. Chapter 14 was graph theory. So I'm not going to go through because I'm going to try to wrap this video up before too long. So any of these definitions I may just breeze through. 49, we're talking about paths and circuits. So that's the answers for those. The edges that connect to a vertex is a degree, or the number of edges rather. And then number 51, which of these is true? Which of the following is true about an edge can be part of a path only once? Okay. All right, so that's 51. Now, on 52, I was looking through them before the video, and in my printout, those first 3 were blanks, so that was weird. So I figured out, based on what's here, what should go in these. So, all right, the question is, how many games are scheduled for Oakland during the week? So here's Oakland. Each of these lines represents a game. And sometimes, can you see that? Yeah. Sometimes it's hard to see, but this little loop looking thing or oval, that means we got 2, that means that Oakland plays Tampa Bay twice. So that's 2 games. New York twice, that's 2 more games. So 4, 5, 6. So we got 6 games that they're going to play. Now, it says list the teams that Oakland plays. Well, I just mentioned them. Any time we have a line or curve that goes to a vertex, that represents a game. So it plays Looks like we're going to play Pittsburgh. We're going to play Philadelphia, Pittsburgh, Philadelphia. Does it play New York? New York. Tampa Bay. Yep, Tampa Bay. Boston. Nope. So it just looks like A, B, C, and D. Okay. How many times does Oakland play each team? So what we're looking at is how many, what's the degree at Oakland for each one? So for Philadelphia, it's only one line, so it plays only once. Boston, there is no path, so 0. Pittsburgh, only 1. Tampa Bay, well, you got this little loop-looking thing. It's not a loop, I shouldn't say that, but this curve, so 2 different vertices, so twice, and same with New York. Okay, 55. Using the vertices to represent land masses and edges to represent bridges, which graph models that city? It's kind of hard to see with the shading, but here's what I'm going to do. I'm going to draw a big vertex for every landmass that we're discussing on this problem. Okay, so only one. So even though North Gothamsville is rather large, it only gets 1 point. Now, I'm going to also draw a curve from each each point to each other. So there's one from A to, looks like they're calling it in, but so from A to North Gothamsville, B to North Gothamsville, C to North Gothamsville. There's also some bridges from A to B, and then B to C, and then A to South, B to South, C to South. And so if I pick this up, if this was a bunch of streams or something, then, and I let North Gothamsville be in, and A stays as A, B, C, and then South Gothamsville is S, then you can see that it looks like this. And then I could even make it tighter and it would look like this. All right, so let's make sure this one doesn't go. Does A go to, so my guess is, all right, we're back. All right, my guess is this one, but I just want to confirm it's not this. So notice there is no connection from South Gothamsville to North Gothamsville. So that's the problem with the second one. Okay, so the answer is A. It's pretty, that one looks pretty obvious. 53, 54, we're gonna do 54 and 55, and then we'll stop this video, which is probably long. 54, same game, same idea. We want to see, we have this house and any room that has a connection like this or a doorway we can connect. So for instance, A and B are connected, okay? And E is also connected to D. Now, I'm gonna just keep going. There's only one vertex on the outside. So I'm gonna put it over here. Okay, so A can go outside, B can go outside. That's our G that it's talking about. Okay, I'm just gonna relabel it right there. C cannot go outside. C is only connected to B. E is connected to B and the outside, F is connected to the outside, and C is connected to F. Okay. So which of these represents our answer? Well, we only have two options. I'm going to check connections, okay? Is A connected to G? Yes, so it happens there. I'm going to probably just do process of elimination. Is, let's see, E and F are not connected. Okay, so A is connected to G and D, and that's it. All right, good. D is connected to A and E. E is connected to G and B, and that's it. B is connected to E, C, G. E, oh, there's our problem. B connects to C, but in this graph it does not. So the process of elimination, it has to be that one. And we could double check it. All right, 55, and we'll stop this long video. All right, so a guard needs to walk a neighborhood, and we want to choose the correct graph. So guard needs to walk the streets of a neighborhood shown in the figure. The guard walks down each street once, using vertices to represent the street. Draw a graph that models it. So I'm going to, so it looks like this is a, okay. Let me just draw my decimal or my points real quick, and then I'll label this. Using, so vertices represent intersections. That's what we got. Any intersection is a point. Well, notice that this graph here is saying that there are two streets that make a loop. That does not happen, so it has to be this one. Okay? All right, so we'll stop the video there and pick up after that.